All right, good morning, everyone. This is day 4 of machine learning fundamentals. You guys have been learning about different things throughout the week, like uh, binary models, data, and tuning your models as well. Today, we're going to be getting into actually deploying it and how you can do that. And then this afternoon, we're going to get into more of LLMs and uh, really looking into how tokenization works. Currently, we have our models outputting predictability, but later on this afternoon, we'll have our models pretty much output the it's going to take a look at what the next token might be after it it goes through that whole process, which we'll take a look at later. So let's go ahead and get started with day 4 AM. Like I said, we're going to be deploying our trained models today. We have one lesson, one lab, and one challenge. Uh, for the lab, we're doing a completely different project just so we can see the workflow of how to deploy everything. But for the challenge, you can use any project you did this week and try to deploy that. We have our TLOs and ELOs. So TLOs save and load trained PyTorch models using state dictionary serialization and deploy a trained model as a REST API using Flask. For our ELOs, the main definitions to take a look at is state dictionary, torch.save, torch.load, model eval, and you guys already have worked with Flask, so you guys know about app.route, decorators, request.json, and JSONify. But we're going to be digging more into that. So today is about taking your models out of the notebook and into the real world. Now that you understand how to train and evaluate PyTorch models, you'll learn how to save them, load them, and serve predictions through a web API. Now, what are we trying to accomplish? We aim to bridge the gap between training experiments and production systems. By the end of this lesson, you will understand how to serialize trained models using torch.save, load them back with torch.load, and wrap your model in a Flask web application that accepts HTTP requests and returns predictions. You'll deploy a simple fruit classifier as practice, then apply the same workflow to your water potability model from day 3 or any other project that you worked on. So are there any questions before we get started with the lesson? All right. So model deployment. The overview, deployment transforms a trained model into a usable service. Instead of running inference manually in a notebook, you save your models, learn parameters, and serve predictions through a web API. Today, you'll learn how to save and load trained models and use Flask to expose your model as a web service that other applications can interact with. Why does deployment matter? Training a model is only half the work. Making it accessible to users and applications requires deployment. So for an example, your water quality model achieves 65% accuracy in a Jupyter notebook, but a water treatment facility needs to check samples from their sensors automatically. They can't import your notebook. They need an API endpoint that accepts measurements and returns predictions. So there are 4 stages. So we have training, saving, loading, and serving. Training, it learns the patterns from the data. So the output is model weights and memory. Saving, it persists learned parameters to a file with an extension of .pt. Loading restores the model for inference. So the model is ready to predict. And then serving, so just serving it on that Flask application. So how do you save trained models? After training, saving the model parameters to disk for later use. You use serialization with PyTorch, and PyTorch provides torch.save to do that. So for this example, we import torch. And after the training completes, so say you already had your project done already, so you would just do torch.save, and then uh, you probably have specified the model that you're using, so that class that you built, and then you're going to add on this dot state dictionary, and then actually save it, save the parameters to this file called waterclassifier.pt. So there are actually uh, so there are actually two methods for serialization. So the first method, you're only saving the parameters, so your weights and biases. So that's done with that state dictionary, but you can also serialize it with saving the whole entire model. So that means the architecture and the parameters. But the only downside to that is that the file size is going to be a whole lot larger and it's self-contained. There's more flexibility if you're just saving the parameters, the weights and biases. You can create a new model uh, within your file and just load those parameters onto it. So an example, think of state dictionary like saving a recipe's measurements without the instructions. You need the you need the original recipe, so the model class to use them. Saving the entire model is like saving the complete recipe. It's convenient but less flexible. So again, parameters is the weights and biases that the model automatically updates during training via back propagation. And then the hyperparameters is the settings you configure before training starts, like batch size, number of epochs, and learning rate, etc. Let's actually go back to this .pt. So that .pt file extension is a PyTorch checkpoint file that stores what you serialize. So it contains a dictionary with keys and values. Keys would be the parameter names, and then the values would be the tensors themselves. Any questions? Okay, so the recommended approach, save the state dictionary for production deployments. So instead of what you saw up here, or did we get into the, okay, never mind. So up here, we saved that model. So we saved the parameters, the weights and biases. We do the same thing down here in this example, but we're saving it to another .pt file. So it's named trained model. And this is just to show this next process. So we're importing pickle, and the pickle import is Python's built-in serialization system. So torch.save is PyTorch's serialization method, and then pickle is Python's. So uh, pickle just turns a Python object into bytes so you can save it and load it back later. Torch.save uses pickle under the hood, but pickle just saves any Python object. Torch.save saves tensors plus Python objects. Let's take a look at, you see scalar over here and scalar down here as well. So scalar is, think of scalar as a single number. It could be 5, -3.2, or 0.0001. It's one value. Thinking about it in math terms, a scalar is one value, a vector is a list of values, matrix is a table of values, and etc. So in our code, it rescales our input features so they're in better numeric range for learning, making the key point or the key phrase is it makes the results more reliable. So think of Pickle as a tool that saves it saves the tool that learned how to adjust any input data. So think of a measuring cup, or think of saving the measuring cup and not just the recipe. So say a recipe says add 2 cups of flour, but you use your favorite custom mug, and the cake comes out perfect one day, but then the next day maybe you didn't wash your mug or something, so you don't have it, so it's not saved. Uh, and then you decide to use a different cup, the cake doesn't come out perfect. Uh, so in this example right here, we use uh, we use pickle so that we can scale it to use different cups or mugs, so that we can still get that perfect output of our cake. Another analogy is, imagine training a model to use Fahrenheit, but later feeding it Celsius. It's the same temperature, but different numbers and completely different meaning. So saving the scalar is like saving the conversion rule, so that it still works and is reliable across the table. Uh, and yeah, at the at this deeper level, it's a lot of math is what it is. But the key point for to know about scalar is it just makes the output more reliable. So over here we have train model.pt. The contents, it's the neural network weights and biases required for model inferencing. And then scalar.pkl, it's a feature normalization parameters, and it's input pre-processing. So loading trained models, when deploying, load the saved parameters to initialize the model for inference. So in this example, we have the deserialization process. So we have our imports, and then we define the same architecture used during training. So we create our model within this class named water classifier. Over here, uh, we're passing in the overall PyTorch uh, model template, and with this super, we're pretty much getting all its attributes and passing it onto this class. And here is where we actually make our network. So we have a sequential network. So we're passing in a feature of 9, and we're gonna get outputted 32 neurons. And then we have our ReLU. That's pretty much uh, hold on one second. So it just adds non-linearity. It's the hidden layer. It lets positive numbers pass through unchanged. So if a number is negative, then it'll default it to 0, so that everything is 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 positive. Think of it like a filter, keep the positive vibes but block the negative ones. And then we have our forward method, and that just specifies the uh, how the flow of the network runs. Over here, we initialize our model, so we're calling that water classifier class. And then since up here we see that we save our state dictionary with the weights and biases. We're now loading it onto this model from that specific file, from that .pt file. And then after that line, we have model.eval. So it's saying uh, it's setting it to the evaluation mode. So it's so this pretty much saying it's done with training and it's now ready to uh, make predictions and ready to use uh, in in simple terms. So next up is our verification. Ensure that the loaded model matches the trained model. So we create a sample input. So we create a variable called sample input and equal it to torch.rand19. So it's a batch of one and has 9 features. And then we also have our output that is calling our model and passing in that input itself. So we print out our input, output, and output value. So our output shape should be 1, 1, output range between 0 and 1. If you trained with, so this example right here is pretty much saying everything needs to be in the same format. So notice how if you have a 932 and then you load it into a model with a 964, it'll give you an error because of its mismatch. So the architecture must be matched exactly. Serving models with Flask. Flask is a lightweight Python web framework for building APIs and web applications. So why do we use Flask again? So it's lightweight, flexible, widely used, and production ready. So next up, we have our example of a basic Flask application. Create a web service that exposes your model for inference. So we have our imports. We initialize the Flask app. We have our pre-trained model over here. And then let's take a look at sigmoid. So sigmoid just squashes the output to a range between 0 and 1, which is perfect for binary classification because it's just zeros and 1. But if you have like a whole range of different numbers, it'll pretty much do some calculations in math so that it it I guess it kind of it scales down to between 0 and 1, if that makes sense. Is there any questions right now? I know this is it's kind of difficult to uh comprehend because there's so much math that goes on in the background, but as long as you understand what's kind of like what's happening in the process of everything, the overlaying workflow, you'll be good. That's why we have a PyTorch. It'll do all the math for us. So after we load our pre-trained model, we do the same thing we did earlier with uh, initializing it, loading our weights and biases, our parameters, and then doing that model.eval to say, hey, this is ready. We have our scalar, and then now we actually get into defining our API endpoints in Flask for model inference. So over here we have a route called /predict, and this just gets input data from the request. So if someone passes in uh, for uh, the water potability example or project, an example would be someone passes in a JSON with different uh, features like pH, uh, it's right here, pH, hardness, solids, chloramine, sulfate, all of this, and it just extracts it in order. And we actually uh, use that scalar to make sure everything will match our model and that our model is able to use it. So the pre-process input is all about getting our raw water measurements into the exact format that the model understands. This inference section is using a trained model to make predictions on new data. And then we're just returning it in a JSON format that's easily that can be easily understood and read by humans. So we have our we have two keys, probability and prediction. So probability is actually the raw score that the model will give back. And then prediction takes a look at that probability score and it'll print out if it's either potable or not potable. So say the probability return 0.87 or something, it'll say that the water is potable. And again, that's done through all this different math and calculations done by the model based on the features that the user passed in. So understanding the components, you guys already know this because you guys have worked with Flask a lot, but we have the Flask name, so we initialize it, create the application instance. We have our roots, so our endpoints, request.json just parses the incoming JSON data, JSONify formats the response as JSON, and then app.run just starts the web server. So the request handling flow, so the client sends the request to the Flask root, and then the JSON gets parsed, it gets sent to a pre-process, a model inference, and then we return that JSON response. Let's take a look at this for each step. So for the step receive request, the code would be request.json. So let's go back up here. Where's that? So that's going to be equal to our data. And then extract features is right here. Pre-process is using that scalar. Convert, we're calling, we're making it into a tensor. And then inference, we're actually passing that tensor into our model. And then after that, we format our response using JSONify to return it back to the user, and it outputs a JSON string. So this is how you would run the Flask application. And then there are two ways to test the API, one using curl and then one using Python. This you can just run straight in your terminal. You're just passing, again, those that object with the keys and values, so those features. And then same thing over here, except it's written out in Python. As always with Flask, you want to put in a health check just to make sure that everything is working correctly and that it is up and running. So load balancers and monitoring systems ping the health endpoint to verify the service is running. If it stops responding, traffic routes to healthy instances. So different frameworks use different serialization formats. We see PyTorch over here using that .pt file extension. Use case is a state dictionary or full model. There's also an HDF5, a saved model, and ONNX for different use cases. Common issues you might see: architecture mismatch, and the cause of that would be model class differs from training. So it goes back to that same example we showed earlier between passing in uh, 932 into a model that has 964. Another issue is missing scaler. Cause of that would be forgetting to save pre-processing. We have connection refused, server not running, 500 internal error, missing input field, and then wrong predictions. The scaler was not applied. So in summary, uh, these are the main things to get out of this lesson. So torch.save, torch.load, and the state dictionary. And you can also pass in the model itself so that you're saving the parameters and the overall architecture. So deployment bridges the gap between training experiments and production systems by saving trained models and serving them through Flask. You enable other applications to leverage your model's predictions via simple API calls. Are there any questions before we move on to the lab? All right. So for our lab, we're going to be deploying a trained model. The objective is deploying a trained PyTorch model as a web service using Flask. You'll train a simple classifier, save it, load it into a Flask application, and test our API. This is the same workflow used to deploy models in production. So let me switch this to my other screen real quick. All right. So first thing we want to do is create our project directory. So I'm just going to call this lab, going to CD into that lab, and then going to uh, first let's set up our virtual environment. So let's do Python 3 env, and then let's just do my env. I see it got created. Okay, now we have to activate it. So source my env. All right, so we activated it. Let's actually open up our VS Code. All right, now what we want to do is pip install Flask and requests. But before we do that, I have to activate my virtual environment again. Let's upgrade pip. And then I'm actually going to create a requirements.txt file, and then just getting my dependencies from one of the projects we did this week and install it just to ensure that I have everything. And then if you don't know how to save your dependencies in a project to your requirements.txt file, you can do that with a pip freeze. That's how I was able to get this 109 lines of dependencies. And then now we can create our Jupyter notebook. So we'll just do a touch. Let's do deployment lab dot IPYNB. So this extension is pretty much short for Interactive Python Notebook. All right, so we created our notebook. Now we have to select our kernel. So to do that, you click on the top right and then click on Python environments and choose your virtual environment. To create a new cell, you can click on this, and then let's go ahead and add our imports. Save it real quick with Command S. And to actually run this cell using your keyboard, you would just do Shift return, and it should run it and give you the output. Okay, so we have this is because we haven't installed this yet, so we actually have to install it using pip install matplotlib. And this dependency is pretty much for it's a Python library for creating visualizations like charts, graphs, and plots. Let's install that. Clear our outputs real quick and rerun this, see what we get. All right, so we got our Python version. So now we're ready to continue. For our next cell, we throw a line in that to specify our seed. So this ensures that the random numbers generated are the same every time we run the code. It's pretty much helpful for uh, uh, reproducibility in experiments, in this case, our lab. So it just helps us with our testing. And then, so let's get into this section right here. So torch.normal creates random numbers from normal distribution. So the apple weight is saying uh, I want 50 samples. So it's coming from this right here, from the size variable. And I want the samples around 155 grams. So that's the variable from the mean. And I want a standard deviation of 15 grams. So I want my apple weights to be between 140 and 170. So there's going to be 50 samples of that. And it's pretty much the same concept for the diameter. So I want my diameter to be 7 centimeters with a standard deviation of 0.5. So it'll be between 6.5 and 7.5 for all 50 samples right here. Torch.stack just combines the weight and diameter into a single tensor, and is going to be a 50 by 2. So it's going to be 50 batches with 2 features for each one. And those 2 features are going to be the weight and diameter. And then the dimension is going to be 1. For the labels, torch.zeros is saying I want to label all 50 batches with zeros. So 0 is going to be, in this case, stand for apples. And then if we look down here, we have oranges. So instead of using torch.zeros, we have torch.ones. So all the labels for the apples or the oranges are going to be 1. So apples will be 0 and oranges will be 1. And then the weight and diameter and torch.stack are pretty much the same concept as above. Any questions on that? All right. So now uh, we're actually combining uh, everything into a data set. So torch.cat concatenates along the rows of apples and oranges, which will give a instead of a 50 by 2, it'll now be 100 by 2 tensor. So it'll be 50 oranges and then 50 apples and then 50 oranges. And then for each batch is going to still have those 2 features, the weight and the weight and the diameter. So that's for this right here. And then this line y equals torch.cat is concatenating the labels into a tensor of 100 by 1. So it's just going to be 50 zeros and 50 ones. And then we're just printing out our data. So let's take a look at what we get. Again, to run the cell, it's shift return. So for our shape, we have a tensor of 100 by 2. Again, that's because of the 50 apples, and then the 50 oranges, and then the two features, which is the weight and the diameter. And then for our label shape, we only have we have 100 batches, but one feature, so it's either going to be a 0 or 1, so 50 zeros and 50 ones. And then here, over here, these last two, we're just pretty much getting, we're counting up the different labels that we have for each different fruit. All right. So now let's actually try and visualize the data. And that's all this is doing. This is that from that matplotlib import. So it's saying create a figure of width of 8 inches and a height of 6 inches. Might be switch around. And then we have our plt.scatter. So this y that squeeze, this specific section right here is or let's backtrack a little bit. This right here, yeah, this right here is saying remove extra dimensions. So from those labels of with the tensor of 100 by 1, it's now just going to be 100. And then if we take a look at the whole thing, that's saying it just creates a Boolean mask that is true for apples. And then this extra 0 selects the weight column. And then if you notice right here, instead of having a 0, it has a 1. That's selecting the uh that's selecting the diameter. So over here is the weight and then diameter. And then we have the label, which is going to be apple. And then this is just transparency. And it's pretty much the same thing over here for our orange. So this line up here is for apples. This line below is for oranges. And then we're just adding labels, weights, diameters, and then a title, our legend. And we're just saying show. So let's just go ahead and run it. We don't really have to dive any deeper than that with it. But here's what we get. So as we can see, there it's pretty separated, but there are some overlaps, barely. So orange, there's some orange points closer to the blue, and then some blue points closer to the orange. So we saw our visualization. Now let's actually define the model. So we're creating that class called fruit classifier. And then we're inheriting from PyTorch's base class. We initialize it, we get all its attributes, and then we set up the network. So over here, we have a 2 because we're passing in those two features, so the weight and uh, diameter. But we're going to be getting an output of 8 neurons. And then it's getting passed to our hidden layer. So again, it just lets positive numbers pass through unchanged and then turns negative numbers into a 0. And then from that output that we get up here, it's getting passed again to this linear. And uh, to this linear layer, and then it should still be 8, but now we want to get an output of just that one, so that that predictability, and then we're throwing in our sigmoid to squash the output to a range between 0 and 1. And again, if there are if there's like higher range between the numbers, maybe uh let's say 50 to 100, or even like let's say negative 50 to 50 or something, it'll squash everything it'll still squash everything between 0 and 1, but since we're doing a binary, everything is already 0 and 1, so it's kind of gonna kind of make it easier and more straightforward. And then this method right here is just specifying the flow of the network and how it runs. So now let's actually print our model and run this cell. So now let's train our model. So the first two lines that we see are that we're initializing two variables called criterion and optimizer. Criterion measures how close the predicted probability is to the true output. And then optimizer uses the atom optimization algorithm that updates the network weights. So it tells which weights to update and the learning rate. Here we just create a list and tie it to the variable losses. It just is going to store the loss at each epoch, and we're looping through 100 times as specified right here. So in our for loop, we have two more variables, so predictions and loss. Predictions is actually uh, sending our input to our model, and then loss is calling that criterion variable and passing in our predictions and then the label. Backward pass is it's the uh the back propagation so that it is able to uh, update the different weights. And then over here, we're just appending uh, the losses into that list. And over here, it's this part right here is just saying in simplified terms to print progress every 20 epochs. So let's run it. So notice how we have an accuracy of 50% for each one. So that tells us that something is not right. So I did some
The
more.
the normalization the normalization step is missing.
Yep. Yep. So where do you think we would put that, Nick?
Before I put it before where you defined your model, though I think you could have put it anywhere before training. I
Yeah.
could be wrong though.
Let's try putting it there. Let's see. Uh, let's try to run it again. Yep, works. So now we have a variety. I mean, they're still all close within the same range, but it's better than all of them being 50. So at least we know uh it's working somewhat. We don't fully know, but like we're getting some varied answers. So
Well, and
uh,
before it wasn't even changing, which was
mhm,
kind of scary because that means it's nothing's happening, right? Versus
yep.
this one, by epoch 20, it's already at 93%.
Mhm,
And then, it crept up from there some too, which is, I think, a good sign.
mhm.
For this slow kid, can you go back to the normalizer and just walk through that?
Yep, yep. All right. So what was happening before was our fruit weights were between like 150 and 250, and diameters were between 6 and 9. So neural network weights are randomly initialized small numbers. So think of zero point zero 0.01, zero point zero 0.02, zero point zero 0.03. So when you multiply uh, each one of those to those weights or diameters, uh, the hidden layer outputs become really huge numbers. So think of it like trying to balance a broom on your finger. If it's too long or heavy, it'll immediately fall to one side or the other, and you can't control it. If it's smaller and more manageable, you can adjust it gradually, and then you can balance it. So normalization makes the number small enough for the neural network to control and understand and use. So this line just does some math to make the feature between to be roughly between -1 and 1, and the center is going to be 0, making it easier for the model to work with compared to like having huge numbers. Let's try, what is 250 times zero point 0.5? Hold on, taking out my calculator.
And
125?
is X in this case the full data set or
Uh, X in this case is the 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 data set.
oh yeah, I see it. It's the tensor. Okay.
Mhm.
Yeah, it's going to take all the values in the tensor, and instead of having them, arbitrarily distributed like 250 and the 7 whatever diameter, it's going to normalize them all around 0. That way, just like you said, kind of like with the broom balancing, if you start with values that are too different, it just fails and gets stuck and never progresses, right? The neural network can't operate when it's got, wildly disparate values like that, like numbers in the 100s and numbers in the, less than 10.
I- Is that so, Nick, you said neural network, but is that not specific types of neural networks? So in this case, the neural network sequential, uh, it behaves that way, or do you think that's a common property across all types of neural networks?
I have no idea. I would assume, I think you can do without it. I was just like Googling off on the side while we were talking about this because I was curious too. And it was basically saying that if the weight or if the initial values are way too out of whack, neural networks can have trouble actually finding a pattern in the data and they just get stuck like it did, where it just sat at 50 and was never improving.
Yeah.
It's
Okay.
like it's so off the mark that it can't even figure out which direction to start walking to improve it. And so it gets stuck. Versus if you normalize around 0, it doesn't overweight the mass and underweight the diameter. It can actually find a pattern in the data and then start, gradient descent walking to the a proper uh, point where it can make predictions that work.
Okay. So that does sound more like a generic characterization characteris characteristic of a neural network.
Perhaps. But you know, there's always caveats and exceptions, so I wouldn't say either one. Someone would prove me wrong.
I thought sigmoid was doing that though.
I think
Uh,
here sigmoid's only doing it at the very end. It's only squishing it into probabilities at the very end. Our neural
oh,
network right now,
very. Yeah,
y-
brother. Okay. Yep, got it.
yeah, it looks, if I understand correctly, this is going to take right now, our model takes the raw values, puts it into a 2/8 linear layer,
Mm.
then it applies rectified linear unit to it, which drops everything below zero and I think proportionally allows weights above zero to exist. Then it passes it to a new linear eight size 8 1, and then at the very end, sigmoid squashes it into a probability between 0 and 1. So the fact that you're passing in these massive, the 220-gram weight and then comparing it to the 7.5 diameter, the 220 just overpowers it so much that it can't make any logical or I guess it's not a logical inference. It can't train itself because it's so far out of whack, it doesn't even know which way to step. If I understand it correctly. Obviously, I'm new to all this.
I think that makes sense.
I dig it. Because the populations were pretty desperate anyway. There wasn't a lot of overlap. So I'm curious, different models will be better depending on your population, I don't know what it's called, um, disparity, your population disparity, maybe.
And then you can't forget, like, this is a simplified example, obviously, but like for example, my little Pokemon Steel type classifier or type classifier, there might not be a relationship between stats and type. And so if there isn't a relationship, then the network's not gonna be able to find it. You know, it might hallucinate something, you might be able to find some, surface level, but as far as it being real, if there's nothing there, you can't find it.
So
Versus
would
this
you,
one,
yeah, go ahead. Sorry.
there's a very, I think it was constructed for there to be a very obvious relationship, which you can see from the graph.
Right.
It's there, there's some overlap, but the majority of it is separated, which is why this thing gets up to a 90 something percent accuracy within, less than 20 epochs or just over 20 epochs.
So aren't we missing like a corollary table in the data exploration phase of this? So we charted it, but we didn't run,
The confusion matrix.
it might be confusion matrix. Yeah, it was just the idea that um, some of the variables, as your Pokemon example state, kind of had, didn't have enough correlation with any of the other features, right? There's no correlation across a high enough separation of values. Um, so nothing correlated into a deterministic feature, right?
Okay.
So I think there's a missing step here in just the data exploration. Speaking out of my depths, kind of hoping Kathleen or Edison would.
I mean, you can, but that's just not how this lab was set up. Like that's if you want to see that context, you can see how the features are correlated to each other. Sure, I think that's something that you could do before building the model.
Yeah, because if you don't know what
But
model
you'd
you're
have, but
get,
you would have to like that would have nothing to do with the model per se, though. You'd have to do, feature, I'm forgetting the name of it, sensitivity, analysis. There's a few things you can run after the model has been run to see what features had the most impact. So you can do things like that. And if at a certain point, like all of them had the same impact or had like very low impact, then like that's something you'd be like, okay, well then there was not really anything to see, and maybe it's not making great predictions or something.
yeah,
I have to look up the actual name for it. Sorry, that's why I'm not great at, I don't speak up because often I'm just not great at explaining things.
I dig it. Sorry for the rabbit hole, Eric.
No, it's a good learning point. Lots of good information there. So is good when we discuss. I think later on too, we're gonna run into another error, so that'll open up more another discussion. So let's see. Let's get to that point. All right. So the next step now is to plot our training loss. So we're pretty much calling the same things as we did for our last chart right here. So let's go ahead and run it. So as we can see, as it's going through the iterations or the epochs, we see that the training loss is minimizing. So next step is let's actually save our parameters using that state dictionary and save it to a file called fruitclassifier.pt. So let's go ahead and run that. So this got created. Actually, I haven't looked in here. Let's see what I can't even read it. Okay. Let's verify that they actually got saved. So we're gonna be getting the file size. So there are some contents in it, so we're good. Now let's actually test the saved model. So we're creating a new model instance using the loaded model variable. We're loading the state dictionary now instead of saving it. And the weights only equals true is we're only getting the weights. We're setting it to evaluation mode. And then we're testing our predictions. And I think this is where we're also going to run into another error. And again, I think it has to do with that normalization. So let's see what we get. Oh, actually, it
Yeah,
worked.
no, it worked, but I think it's wrong here.
Uh,
Because see how it's 0% chance? I
mhm.
don't know if this model, I mean, sure, but I don't think it should ever get a 0% chance. Because when I first ran it, I had the opposite issue. I was getting 100%
Oh,
every
really?
time. And I think
Mhm.
it's because the test right here doesn't normalize the data first.
So you think we should put that same line that we tossed in up here a little
Yeah,
bit?
which is that tensor 160.
You said what?
Sorry, my internet was being weird.
Uh,
So the model is expecting normalized data because that's what we were trained on. But if you go to the test down at the bottom, do you ever normalize that test data that you're inputting?
no.
I think that's the problem. I had that same issue too. And that's
Yeah,
when it gets very certain that it's one way or the other, which I don't think these models should ever be, 100% or 0%.
yeah, let's test it out. Because earlier when I was running it for the
Like
first time, it was giving me the opposite. I just kept on getting the prediction to be oranges.
orange
Yeah,
100%.
yeah.
Yep, me too. No, so I don't think what you're doing here will work because the model is already fine based on what we did earlier. I'm saying that this line right here, test underscore fruit equals torch
Mhm.
tensor 167.2. And then what you're doing is you're passing that to the model. And the model, no, hold on. What did I
You're
do?
saying you need to normalize the test fruit first?
Yes, you need to do some sort of transform. You need to do a normalization after test fruit is called or somewhere on that line because the model isn't expecting that. It's expecting normalized data based on
So
what we did earlier.
you could change X to test fruit dot mean and test fruit dot std.
Oh, okay. Yeah, yeah,
I,
that
I
makes
think so.
uh,
Exactly. Yeah, yeah, yeah.
Okay, I think this might work because earlier I was trying to transform this into a different type of data. Just throwing a comma over here and then transforming it. Let's see if this works.
I'm sure there's 20 ways to do it. Typo. Yeah.
All right, let's see. Not a number.
Yeah, because one of your x's is, I don't think you're changing out all the x's here in this.
Let me see. Test fruit minus. Let's try leaving this as x. Let's see. Hmm. All right, that seems more correct. Let's run it
I don't
again.
think it's perfect. Yeah, it's getting there, but I don't think it's perfect.
Yeah. All right. What do you guys think? You guys want to modify some more? You think it's good at the moment? I I say it's I say it's all right because we're not getting zero over here or 100, so it's doing some sort of probability and prediction.
What is x dot standard output actually referencing then in this?
Uh,
So it's standard deviation, right?
Hmm.
yeah, I believe so.
So
Can, can you get rid of on that line you have highlighted, the
Mhm.
third test underscore fruit and put it back to a capital X? Now run it? No, it broke it. My bad.
See what happens if we change this to X.
I think X as well need to be test underscore fruit.
You said which one?
X,
This one?
yeah.
Well, when we did that the first time, it was saying it wasn't a number. Let's look at it again.
Oh,
Here. Wait, degrees of freedom is less than or equal to zero. So it's
is X representing the training data?
yep.
Yeah, X is a tensor, right?
hmm
And so scroll up what you're doing.
So the problem with this, apparently, I put it in the chat, is that using this line to normalize one tensor, like the problem is that like the standard deviation and mean for it is always going to be this input value. So the
Yeah.
result's going to be 0. So that's not going to be helpful in this context. So the solution is to use the mean and standard deviation from the test. Yeah.
The training,
Or from the training data. Yeah.
that should be X.
So test fruit minus, yeah, then X dot
So
mean.
the second two
X
test fruits
dot.
should be X, right?
Yeah, but the first one
Yes.
should still be test fruit.
Yeah, see that broke it though when we did that just a second ago.
Hmm.
You're saying like this, Kathleen?
And the
Yes.
last one,
And
right?
the
And
last
the
one.
last one.
Let's see.
And it didn't work.
I don't think we tested it yet. Let's see.
Yeah, we did it and it did this.
Hmm.
Had
Trying.
you cleared the results, Eric? Is
Yeah.
x still holding a value?
I mean, it has to be because all it's doing is X is a tensor and X dot STD parentheses is pulling the standard deviation and X dot mean is just pulling the average. What is the dim zero equals? Dimension zero? Because mine doesn't have that. But mine could be wrong.
Yeah, seems like the only way we were getting uh reasonable probability was when we had test fruit over here and then X over here.
Likely an apple. Would you let's try changing the data in test fruit, the first line, the 167.2. What is an apple or what is an orange? Do 240 and 8.5. Let's see
40.
what it says. Yeah, 240 and 8.5. That should be solidly an orange. 8.5, yeah. Now run it.
No, nope.
It came up with the exact same thing, right? 34.9, and it should have changed. Wait, test input. Did the test input even change? That's weird. Did you run the cell?
Yeah, it did. Let me.
It won't change because test.mean is the same as earlier, which is 0.
But right there, that output, that test output equals 160. There's no way that's right because we just changed it to 240 unless
Let's try.
something
You think we have to rerun everything?
couldn't hurt.
Yeah, let's try.
Maybe it could. I don't know.
I mean, it wouldn't hurt it. It would just reset everything. Yeah.
Nope, still. Oh, wait, hold on.
Probability
That's
did
button.
change.
The
Oh,
weight
because
of
test input is
diameter.
hard coded. My bad. Right there in that printf statement, the test input, the first print.
Oh, okay.
Yeah, so we can ignore that line. That doesn't matter. But we are
How
up
do you
to an
think,
orange now.
how do you guys think we could get the actual weight and diameters passing in?
The same way,
Test fruit. Think
bracket.
Test fruit brackets 0, 0.
uh,
Oh, I
you
don't
said
know.
you said what? Bracket zero.
Test underscore fruit,
Let's see.
open bracket, parentheses, yeah, parentheses.
Or would it be a square
Just do a
bracket?
bracket zero
The
and let's see
square,
what it
yeah.
comes up with.
Yeah,
Bracket
square.
zero and then run it and see what
Then
happens.
0, 0.
You said 0, 0 over here?
Yeah.
Let's see. Oh, let's try. Okay, what is it?
All right. Oh.
Hmm. All right, it's
Oh,
gonna
okay.
be the
Yeah.
tensor, but why is it 0 point?
Let's see.
Yeah, I don't know what methods you can do on a tensor to pull
And
data out of it.
tensors, yeah.
I'm sure it can be done, but
See real quick.
it'll also probably chime in about our normalization being incorrect. Because there's no way we should be using test underscore fruit mean average right there. I don't think. That doesn't make sense to
Oh
me.
yep, exactly.
Did it chime in and say something about it?
Oh no, but yeah, I agree with what you just said though. Just taking a look at
We
this.
had already changed that to X though.
Yeah, and it breaks it for some reason. Right now, I don't think it's right though either because the probability it came up with one, but it's barely in the orange category, and the number I gave should be very solidly in the orange category. I picked it from the more like for sure orange, and it might be correct, but I don't think it should be on the fence like that. I think it should be like, hey, yeah, 85% chance this is an orange. That's just me glancing at the graph. I don't know how reliable that relationship is.
I don't know. Okay, there we go. So I pretty much just gave it the whole code snippet, and then I was like, how do I change this line to the weight I am passing in with my tensor? Great question. This Okay, it's giving us a shape. Yep, it should be 1, 2.
Looks like Edison was right,
Yeah.
but
Print.
oh, you have to.
Uh,
Yeah, there is another dot item method you have to put on it at the end.
dot.
What's the dot item G? Oh, gram. The G is gram. Okay. The first one was 00.
All right, let's test it out right now. Still giving us that 0.0. Okay, this goes back to that to this line right here.
Yeah, see, we had it right, but why was it breaking? I think it's making an assumption there that X mean and X standard are somewhere else in the file.
Yeah. Gonna
It's not
I was thinking
necessarily
change.
true.
Yeah, I was thinking about changing these two periods. Let's see what happens.
Yeah, they're not defined in the file, I don't think. X standard.
So I think it's just our training set is so um the classes in our training set are so distinct. I think it's just a really confident model. And so I think for your probability, maybe if you do 0.00000
There we go.
to like,
Wait, why did the weight work all of a sudden? 240, so it got it right. So what was the difference between this and what we did earlier? I swear that looks exactly the same to me.
Yeah, right.
Maybe there was like parentheses. No, I don't know. That's weird. I'm sure it's something super obvious. It usually always is. But yes, if you would, what's the probability of it being a orange? Orange
At 100.
100%. Jeez. Okay. Oh, and Kathleen, you were saying that it's probably like if we went to more decimal places, there'd be like a 99.999, but not quite 100.
yeah, I think so.
Okay. But just the way we're going is keeping it. Okay.
All right, you guys want to test out some different numbers?
185, 7.5. That's kind of on the boundary of apple and orange.
I don't know why it gave us.
So many decimals.
Okay. How come it's
See, it says 100% orange, which definitely should not be the case.
Yep.
See, something. So it didn't fix it. Why? Are we normalizing twice on accident? So
What do you mean?
earlier in the file, capital X, did we apply a transformation to it when we normalized it? We did. So we already did the transform and we're doing it again down there, right? Because right now X in our file, capital X is, yeah, this line right here that's highlighted. It's already had the transformation applied to it. So
So this is how I have mine. So like after you make the
Yes. Yep.
X and then so making the mean, making the standard, and then normalize the data set. And then did you add that into your like the for loop for the
No,
tree?
no. This is correct. What he did here was correct. I'm just saying right now, capital X after the line he has highlighted
Mhm.
has the normalization applied to it, right?
Correct. Yeah.
And what we're doing down below is we're trying to apply a normalization again to it a second time. And I think that's screwing things up. So we need to
No,
do,
for
no?
the because you're applying you're basically uh hmm. So you're saying the
You think
So you
Kathleen's
think,
code
maybe
is
if you use
good.
a different if you
oh
use a
yeah,
different
yeah. We
name
normalized
for it,
twice.
like
Yes.
X scaled there, and then so that way you're not calling the variable again.
We basically need to capture the value
We
of
need to
X
capture the mean
mean
first.
and X STD here and then use it later. What we're doing
Yeah.
currently, I think, is we're normalizing twice, which is breaking it. So, Eric, let's
Mhm.
try it right above this line.
Yep.
Make a variable X underscore mean
Yeah, I
or what?
just put it in the chat. I don't know if you wanted
Yeah,
to
just like what
copy.
Kathleen
All right.
showed. And that should be equal to X. Yeah.
Yeah.
Parentheses dim equals 0. And then we need to make another variable. Yep. X underscore standard or whatever you want to call it.
And then X scaled.
Not even. So
X scaled would be the one below.
yeah,
On
your
here.
next line. Yeah, that
Yeah.
guy is X scaled. And we can change the values in there for I guess to use X mean and X standard if we want. Or I think you can actually just leave it alone and it'll be fine. We just need the X mean and the X standard for later, way down at the bottom. We need those. So we don't try to rescale the data a second time. Because I think that's what's breaking it. X mean X
Yeah,
standard.
so you do want to change your X variable back up there to that
Okay.
X underscore scaled equals.
Yeah.
Yeah.
I'll have that. Yeah. X underscore scaled. Yep. Then everything should work fine now without changing the one we have below.
So leave these as
Oh,
what I
then we
I would
didn't need to
change
make
this
those
to
variables.
I
Yeah.
would
We
change
don't
it
need to
to
make
like
those variables now since we have the X scaled.
So
so I would change this to X scaled.
no,
No.
because then we'd be scaling it twice. So we're trying to do two things at once here, and there's two methods of doing it, and we shouldn't mix them because that's confusing. So as your code stands right now,
Mhm.
will that work?
I
I
see.
don't like the addition. Go up to that X scaled that you did just now, if you would, please. Get rid of the underscore scaled. I don't like that. Now go to the bottom of the file and change X, the capital X dot mean equals dim 0. Change that to X underscore mean or whatever we named the variable earlier and get rid of the dim equals 0. And that's what we named them. X standard, X mean. Okay.
Yeah. Yeah. That's right.
Now we have to run from the top to create those variables.
Yeah. All right.
Yeah, those are the values after they were scaled.
I feel like
And
this.
45% is about right. I picked about halfway through the graph. So that sounds, so I would also, we could just do some more obvious ones. Do a 140 and a 6.5. This should be a strong apple. Yep.
Nice.
And then, a strong orange could be 220 and 8.5.
Nice. Yo,
That's looking right to me.
yo,
Can you go
good,
Yeah,
back to
good
your
work,
strong
guys. Good
apple?
work.
Can you go back to your strong apple? Was that, I
Which one?
think I read it. It looked like it was just 0.3 for probability.
Oh,
probability of being an orange, I think. 0.3 is what it said.
yeah, I think so. Let's see.
Oh, okay, then that makes sense.
Yep.
Yes,
Yeah, it's
gotcha.
whatever. Yeah, it
Yeah,
changes
it'd be
kind of with the
90,
prediction.
99.7% probability of being an apple.
Mhm.
Uh, yeah, awesome.
Yeah, great work, guys. Great work.
I guess you can't normalize data twice. That screws the whole thing up.
All right. So anybody want to take a stab at trying to explain this again? So why do we put these variables up here, the x mean and x STD? So
So we can use them later. Because what we were doing is right there on the line just below where your cursor is, the
Mhm.
x equals, yeah, we're transforming x. So it's been normalized. So we can no longer pull the x mean and we can no longer use x dot mean dim zero and x dot standard dim zero later in the file because we're not pulling it from the actual data. We're pulling it from the data that's been normalized, which I guess what you would be trying to do down there with the test data is we're normalizing test data, trying to normalize test data using data that was already normalized, and that doesn't work. It wouldn't squash it properly.
Mhm.
And so we were getting probability values, but they were completely wrong. I'm sure they were way, way off.
Can you go back up, Eric, just a little? And
Mhm.
X here is defined as,
Where like right here or
The
up
big
somewhere
capital X,
yeah, so we've got X dot mean. Where, yeah, where is X up here?
right here.
Okay, so which is the combined data set,
it's just a
a
tensor.
tensor,
So
right?
it's a big a whole bunch of numbers of numbers of numbers potentially. Actually, I think our data is so simple here. It's just a matrix, right? Or two dimensional. It has
Yeah.
a diameter and a weight.
Or actually it would be one dimensional because so it's pretty much what so it'll be
So it's not a scalar because a scalar is a single number. A vector
it's
is
an array within an array, isn't it?
it's just an array. And then a matrix is a bunch of arrays inside of an array. And then one step further, one dimensional further, you start getting what's called tensors. But then again, they're all tensors. Some are just lower dimensions than others, in my opinion. But either way, sorry, I'm probably talking a lot. Troy, as far as I understand it, X is just all of our data. It's just a giant block of numbers.
Yes. Well, yeah, we set this up for the labeled set as being a different set of data. So yeah,
Yes.
yeah, yeah, it's all the unlabeled data. Got it.
Anybody have any more questions? Nope. Okay. Let's try to finish this lab. All right. Now we're just going to be creating our Flask app. So you guys have seen this before. So or import your dependencies. So for Flask request and JSONify, we define the model class. We initialize Flask. We load the model. So we do that by using load state dictionary and specifying the file to load from. We do model.eval, specify our routes. So the / is just a health check endpoint. And then the predict is actually making our calculations. and we have the app.run all the way at the bottom. So let's go ahead and try to run this.
You put it in the Jupyter notebook. It needs to be in a separate file,
Oh,
right?
yeah.
What would happen if you ran it? What would it do inside the Jupyter notebook? It tried, right? And then
Yeah, I could have sworn I ran it in my Jupyter notebook earlier.
I mean it looks like it's
Oh
trying
yeah,
to what but it hits an
actually,
error.
yeah.
What's the error? Address is already in use.
let's let's try clicking on it. See. Oh,
It's because we are running in debug mode, I believe. So we are running the app in debug mode, which calls itself multiple times.
I feel like I didn't close out my server from earlier. Let
Yeah,
me.
like it's like that port is already occupied by something and it's yeah, I mean that's what it's saying, right? That port's already in use.
Yeah, yeah. That's what it was saying. Like check to see if I is already. Let's see. I don't know what those are, but we'll kill both of them.
What about the
Uh,
port that it called out? It called out 9012, 9012.
you wanna let's check that one?
LS of yeah. Because that's what it's complaining about. It's saying something's there. Maybe like Flask spins up additional things in the background and one of them got stuck or is still running. And so now not I don't think the port 5000 is the problem, though I could be wrong. It looks like something on port 9012 is the problem. But I don't know what that is. Could be important.
Uh, hopefully this doesn't mess anything up. Let's see. 58757. All right, that was the current one we were running. Let's see again.
Could that look like your something from your Jupyter notebook?
Yeah, I think it was
What
this.
about
Like it started
PID
up server.
29453?
Yeah, it's
Oh,
not even there anymore. Let's see. Check 5000 again. Did anybody get it to work on theirs?
I didn't try in the Jupyter notebook.
For the lab,
Mhm.
yeah, mine works.
Did you run it from a Python file or?
No, I followed the lab directions exactly. So
You put it in app.py.
yeah, app.py.
I'm
Yeah, and I didn't run
wondering.
into any errors.
All right, just check if it works for you guys too. It worked for you, Nick?
In app.py or in a Jupyter
Uh,
notebook?
Jupyter Notebook
Let me try.
or
App.py worked for me.
Okay. Oh wait, yeah, that's because okay. I think we were supposed to create an app.py. Yep,
Yeah, that's
yep,
what the
yep.
lab says.
All right, yep, yep. That was my mistake. All right, sweet. Okay, so now if we click on that link, it does work.
You should get the healthy thing, right?
Mhm.
Yeah.
And then now let's run these other commands in a new terminal.
It,
So just check the health endpoint. Yep, healthy. And then let's test out our prediction.
it should not work because you need to normalize the data, which the app.py doesn't do. So we need to add some code to app.py to normalize the data before it passes it to the model.
Just making the same adjustment that we did in the
Yeah.
lab, or the previous.
Where was it?
I had to do some extra steps to pull those values because those don't exist in app.py.
Is it the import? Let's see.
I,
No.
what me and the LLM
Mhm.
basically as in my Jupyter notebook, I added another save. Instead of just saving the model, I also saved the normalization params in a .pt file. And then I load that normalization params.pt and pull the mean and the standard and then use them for normalizing the data before passing it to the model.
So you
Because
saved it,
otherwise, go ahead.
you saved it over here?
Let me see where I did that. Okay, I added a new code block
Mhm.
inside my uh, Jupyter notebook with this code right here. So wait, so the fruit classifier, so line 1 and 2, one's a comment,
Mhm.
line 2 is should already be in your code. The second torch.save, mean and standard, that's the one you want. So the only line you really need is that torch.save, mean standard. Get rid of lines 1, 2, 4, and 5. Those are the only thing you need is that third line.
Oh, this one right here.
Yep, yep. That just saves those values so app.py can use them for normalization because it doesn't have big X. Big X only exists in the Jupyter notebook, right?
Mhm.
And so
Yeah,
you
and
need
then
to we need
load
to
it up.
run that so it saves it. Is that not what we called it? X mean, X standard.
We'll have to rerun everything. Let's see, or just this.
There we go.
It's-
Yeah, see over on the left-hand side, we've got normalization underscore params. Yeah. So now those two values are just saved inside there. I'm sure that you could do this a lot of different ways, but that's what the LLM suggested to me.
Then it would be torch dot load. No, wait.
Yeah, literally model it exactly. If you go to app.py and you look at your load state dict for the model itself, further down.
Oh, right here. Yep.
Yeah, so we're gonna do that again, except instead of loading fruit underscore classifier.pt, you load normalization params.pt. Leave weights only equals true, and then
Yep, that should work, right?
no, we have to no, almost. There's one more step. We have to extract the mean and the standard deviation from that newly loaded file. So right there, scroll up a little bit more, right there. Okay, X mean and X standard, those equals right there. We can get actually no, leave those. So X mean equals everything after it should be whatever you called model dot. Oh, line 20. Make a variable called like norm params or something. Yeah, norm params equals that. Now, X mean should be equal to norm params bracket mean in quotes. Yeah. And then same thing for the next line. Norm params bracket STD should be XSTD. That's what we named everything, I think.
Yeah, just get rid of this one, right?
Yes, and now we actually have to implement that later in there. Data input tensor, blah, blah, blah. Okay. Inside the route define predict. Is that where you are?
Yep.
Yeah, yep, okay. After create tensor, but before make prediction. Yep. Make a variable. I called it input normalized. Input normalized dot item. And then it's input underscore tensor. Is that what it was? Yep. Input tensor surrounded by parentheses minus x mean. My bad. There was before input tensor, open parentheses. So we got to do that same operation where we subtract the mean and the divide by the standard deviation. Yeah, yeah.
Like this.
Yep, just like that. Just like that. Except, yeah, test fruit should be input tensor. And is x mean and x standard what we did for the variables? It's not throwing a linting error, so I assume that's
Yeah.
okay. And then
Mm.
that looks right to me.
This one would then be input normalized, right?
Correct. Yep, yep. Yeah, otherwise it wasn't being used. And then the rest of it looks the same to me.
All right. Let's test it out. Actually,
Yeah, I think we named, wait, in-state mean standard. When you, I don't
oh,
think we can use double quotes. Maybe?
over here.
I think, does it have to be single quotes? Is that a thing? I forget my Python basics. Is that what it's complaining about? Missing keys in state device
Let's try it.
classifier model.
Or there's actually output by the saved model.
Normalized params should be. I think it was the very last piece of code. And yeah, mean and standard. We're putting it into there. So it's there,
Mhm.
I think. I think it's complaining about something else. Keys in state dig. Oh, it's loading state dict for fruit classifier. Hold on. Let me see what mine did.
Oh, no, that should be correct right here. What line is
Oh,
it?
so model equals fruit
Do you
classifier,
have to
yes.
do you have to load the normalization params dot PT also? Well, you did. So norm
Yes,
param.
on line 20. But the line 19, what is line 19? Why are we loading it twice? Because we already do that, right? Model equals.
Oh yeah, down here, right? Yeah. So
Oh,
we should move this to that endpoint, you think? Lines 24 to 20?
no. Go. App equals fast. So if you would scroll to the very top of your file.
Mm.
So you got your imports, then you define the model. Yes. The class. Okay, scroll down a little bit. So the next thing you do is model equals fruit classifier. Yes. Okay. We're saying the model is the fruit classifier here. We need to load the fruit classifier.pt file. Where do we do that? We do that later?
Yeah, over
Right. Oh, right
over
there.
here.
See, we're doing the model equals fruit classifier twice. Why are we do? I don't think we should be
Okay.
doing that.
All right, yeah.
So
I
let's get
think
rid of the
we
one up
should.
top.
Yeah. And then let's move this right here below.
Model params equals. Yes, the model eval. So we also have two model evals. See on line 27 and line 31? I
Yeah,
don't think that's right. I think we only need it once. Okay. And then norm params equals.
maybe move this to. See.
I think line 26. Do we need that?
Yes, we have
Yeah,
to load in the
the
training.
parameters. Yep.
Yeah, the parameters. So because we have the model, but we don't have the parameters until we import that. Oh, here right here,
Yeah.
line 28. Norm params model.load. No, norm params equals torch.load. Oh, it's double wrapped. Why do we do that? It get rid of the outer print. Yeah, okay. Get rid of that last parentheses
Mhm.
and then get rid of everything in front of torch up to the equal sign. Torch.load. Because it's not a model. We're just pulling in
Oh, okay. Yep, yep.
torch.load normalization params. Mean standard. Okay, let's try that.
Sweet. All right, let's try that curl again. That seemed correct. Let's see.
For a weight of 150 and a diameter of, what was it?
7.
Yeah, that's solidly in the middle of Apple, at least according to the graph.
Let's try a different curl. Let's
That's the
do
same one.
orange.
Oh, just gonna change the numbers.
Yeah.
You want a solid orange or you already got numbers?
Yeah, you got one?
Yeah, let's do 220
Hmm.
and 8.5. So this one should be very orange.
Yep.
And then you want to do one kind of on the edge, not sure. Be 180 and 7.5. Still says pretty solid apple.
Yep.
I guess I did probably pick it closer to apple, but it's not so sure. It's got that 34%. That's about what I got, I think.
Okay.
So either we made the exact same mistakes or maybe it's right. Maybe a mix of both.
I'm happy with it.
I mean, it provides an output, so
Mm,
success.
Well, and it's not 100% or 0% all the
yeah.
time, you know? That's good.
All right. We're a little bit, well, not a little bit, but we're over our lesson, but that was good. That was good. So let's just try to finish it up real quick. I'm gonna do that. So yeah, what we built today was the uh our notebook, and we used it to train and save the models. We built uh two files where we could save and load from. So the fruit classifier and then the normalization params. So key takeaway, be mindful of the normalization because that can mess a lot of things up. And then we created our Flask server, and key concepts are torch.save, torch.load, and then model.eval. And you guys know these already. So are there any questions? I think that was pretty solid. Great work, everyone. You guys did good with troubleshooting, and we got it up. So I feel like that was a good lesson. But for the challenge for today, so if if you haven't gotten that code to work on that. If you did, go ahead and work on your water classifier, or if you did another project, work on that, trying to deploy that. And yeah, just go ahead and take your 15-minute break. We'll come back at 1300 for our day 4 p.m. Lesson, and at uh 3 p.m. CST, we will be doing a retro as well. So does that sound good, everybody? Sounds good, Troy. All right. And again, great work. All right, let me stop sharing.